Okay, this is Dr. Holt. In this UT problem, I have a 3.7 kilogram mass. It's being pushed to the right by a force here. I have a coefficient of friction here of 0.27. I have a coefficient of friction between these two surfaces of 0.47. I have a 0.7 kilogram mass here, and obviously the acceleration of gravity is 9.8 meters per second squared. Now this problem here, you want to find out what is the minimum force F that must be exerted on this block here in order that the 0.7 kilogram mass or block does not fall. So the first thing to do the problem like this is to draw yourself up two free body diagrams. And if you try to do this without, I mean, you're just really going to struggle. So the first thing is to do one of this. I come over here. I will draw my force of gravity coming down here. So that'll be my force of gravity. Again, that's going to be Earth onto the 0.7 kilogram. And that value is going to equal to the mass, 0.7 kilograms times 9.8 meters per second squared. And that's going to give me a value of 6.86 newtons here. Alright, I'm going to have a force here going to the right, and that is going to be the force of the 3.7 onto the 0.7 mass. Alright, now I'm going to have the force of friction. And remember, if this object does not slide down, then friction has got to match. So these have to have the same magnitude. So here the friction, which is not going to slide, it'll be static friction, is going to equal to 6.86 newtons. Alright, and then to the right, off to the side, I like to do my mass times acceleration, and that's going to be 0.7 kilograms times my acceleration. At this point, I will write my equation, the summation of forces in the x is equal to mass times acceleration in the x. Now, there's one thing to note here. You know what the coefficient of friction is here. So since we want to find the minimum force, F, then can we not say that the frictional force, the static friction, must equal to the normal force times 0.47 being my coefficient. Okay. Now I know my static friction is 6.86. So I put 6.86 newtons is equal to this one, and now my normal, okay, my normal force is going to be this guy right here, right? That's what's pushing on this object. I should have really, let's change this, the terminology just a little bit. We'll call that F normal, and that again is going to be the 3.7 pushing onto the 0.7. So can I not say that's going to be my normal force times 0.47? I will take 6.86 newtons, I will divide it by 0.47, and I will get my normal force immediately. Let me grab the calculator real quick. 6.86 divided by 0.47, that gives me a value of 14.60 approximately. Well, that's going to help me immediately find my acceleration, because when I sum the forces in the x, my normal, which is going to be that value, 14.60, is equal to my mass, 0.7 times my acceleration in the x, or you make it just a, it doesn't really matter. So when I do this value, I take 14.6 divided by the mass of 0.7, I will get an acceleration of a value of 20.85 meters per second squared. Okay. Alright, so now that we know that, we will go back and draw another free body diagram. Go ahead and erase this. And we're going to draw a free body diagram right through here. Alright. This one's going to be an interesting pre-pi diagram because it's a little different than what we've done in the past. So that has 3.7 kilograms. So I come over here, I draw the force of gravity coming down, force of gravity of the Earth onto the 3.7 is going to equal to the mass, 3.7 kilograms times 9.8 meters per second squared. Let's see if I have that number, which I guess I thought I had run that earlier. I guess I did not. So 3.7 times 9.8. That gives me a value of 36.26 newtons. Alright, now this is interesting here. Let's think about what's causing this friction. I should have actually labeled that. That static friction is actually here. Isn't that going to be the 3.7 onto the 0.7? That's what's causing the friction. So I'm going to color these so you can see these. Make this one into a red. It's going to have a force pair. If it goes up here, then it must come down here. So this guy here is going to be the static friction of the 0.7 onto the 3.7, and that's going to be equal to what we said was 6.86 newtons. So if you forget that, it's really going to mess up your normal force. So now we do our normal force. Okay, now you have no other forces in the vertical direction, so your normal force must be the magnitude of those. So we'll run those to the calculator. At 43.12. Again, and what that normal force is really is the lower surface. We'll call this S, and that would be S onto the 3.7. all right, now let's see what else I have. And I'm going to color these because I want you to make sure that you understand that these are force pairs. This one here, and I'll draw a line from the red all the way over to there so you can see where those force pairs are coming from. That is a force pair. One goes up, the other goes down on the other object. Alright, I also have a force F going to the right. Let's change this black. Again, that's coming from the picture right here. Now I have this normal here. That's going to cause another force pair, so we're going to color that so you can see that. I'll make that one purple. So it must go back the other way. Like that. And I'm also going to have a frictional force. So let's go ahead and now we know what that normal force is, right? We got that normal force here as 14.6 newtons. I'll come down here, 14.6 newtons. I'll label that actually as the normal force. That's going to be the normal force of the 0.7 onto the 3.7. And again, that's going to equal to my 14.6 newtons. Alright, now let's figure out what the friction is. Let's go back to our picture. Alright, now since we have acceleration, this value here is going to be a kinetic friction, and I mentioned too that one would be static because it's not sliding down. So I will take my normal force, because we know normal force times coefficient of my kinetic friction will give me my kinetic friction force. I take 43.12, which is my normal force. I multiply that by the coefficient of friction that is given, a 0.27. And that gives me a value of 11.64. And then over here, again, I always do this. I take the mass of the object, which is 3.7, and I multiply that by the acceleration. Now we know what the acceleration is. We know it's 20.85, so we'll take that right back out. Because remember, they're in contact, so they both must accelerate the same, have the same acceleration. All right, now we're ready to write the equations. And look what happens is we only have one unknown. The only thing we don't know is F. So write this all out, we will get minus 11.64 newtons. And what I'm doing here is I'm summing the forces in the x. And I should write that down for you. Sum forces in the x direction. I'll set it equal to mass times acceleration in the x direction. That's all I'm doing. So I get minus 11.64 minus 14.60, because this one's going back this direction here, plus F is equal to 3.7 times 20.85. Okay, so now I move these to the other side, I solve for F, and F, I will get a value of 103.39 newtons. Okay, let me just check that. I had run those earlier, just make sure that is correct. Plus 14.6 plus 3.7 times 20.85. Yeah, exactly, 103.39 newtons. All right, good problem. Probably, let's go back through. I want to identify color coding one of these other force pairs. This one was purple here. Again, that was my normal here, so I'd have to come back here and make this one purple. Okay, just from past experiences, the one thing I notice that students usually leave out is when they draw the free body diagram of the 3.7, they forget to add back this force here. Remember, you're looking for force pairs when you do this. You've got to ask yourself, what is causing the static friction? When you're drawing the one here, it's the 3.7 onto the 0.7. So then when you draw the 3.7, you must have a one in the opposite direction, the 0.7 onto the 3.7. Anyway, I hope this video was useful. I wish you guys the best of luck on these problems.